In this video, we're going to discuss the graph of a rational function. I'm going to be using the Desmos graphing calculator to assist me with this. You may be using a TI-83 or 84 calculator for this instead. So we're going to try and put everything together here where we try and determine the domain, range, intercepts, asymptotes, and any other interesting things that go on here with the rational function, and put those on a graph and be able to sketch the graph, because the scale is so different on all of these. Here I'm going to try and just use the Desmos graphing calculator and zoom in and out as necessary. And I'll show you the interesting points that we're going to want to find along the way. And I'll talk about how to arrive at some of those numbers algebraically. So the first function here is going to be f of x is going to be equal to 3x divided by the quantity x plus 1 divided by x plus 5. That's going to give us two vertical asymptotes in the graph. There's going to be a vertical asymptote here at x equals -1. Domain, just so we know that, is going to be x is not equal to -1 or -5. There's vertical asymptotes at x equals -5 and x equals -1. We're going to have x-intercepts here at 0, 0. That's also going to be our y-intercept. We have a horizontal asymptote at y equals 0. So we can see that the graph is going to cross the horizontal asymptote at 0, 0. We're also going to be interested in this minimum point right here to help us graph, and that maximum point right there to help us graph. We'll round them to a couple decimal places like we've done before, probably to the nearest hundredth. But in order to get it on your graph paper, you're going to have to know how low it goes and how high it goes there. Because we know that it does not cross the horizontal asymptote anywhere other than at 0, 0, we can stick in some test points here. Again, I'm just going to mark this up that there's a vertical asymptote here. X equals to -5, x equals to -1. Those vertical lines, it's where it approaches but doesn't touch. I want to make them be broken instead of, there we go. And same thing here. I want this one to be broken. Let's make them all the same color here, so that they all look like they're part of the same graph. So those dotted lines there are not actually part of the graph, they're just boundaries. I'm also going to show you the horizontal asymptote of y equals 1. We're going to make that broken as well. I'm sorry, y equals 0. Okay. So you would have something like that on your paper, and it's going to be your job to sketch the remaining pieces here, given that you know the x-intercept. There's going to be a y-intercept when x equals 0. Let's find what f of 0 is. It is 0. So the x-intercept and y-intercept are both right there at 0, 0. We've got our domain We could figure out our range. It's a little hard to figure out here because we're not going to have any numbers between this number and this number. But you could figure that out, round it to a couple decimal places and give your range. And algebraically, if we wanted to prove that the function crossed the horizontal asymptote, which it can do, we're going to take the function, going to set it equal to the horizontal asymptote. When we multiply anything by 0, we get 0. And so it's going to cross the HA at x equals 0. Again, I'm going to let Desmos do all the graphing for me today. It makes much better graphs than I do, but you can sketch that picture on your own graph paper if you desire. Now let's go on to the next function. We can see that we're going to have a oblique asymptote here at y equals x. We have a vertical asymptote at x equals 0. We have x-intercepts at -3, 0 and 3, 0. We have no y-intercept. And we're not going to cross that oblique asymptote in this case. So you can go ahead and use your graphing calculator to help you get some additional points in each region to see what this graph is going to look like and sketch that graph. Again, let me show you the oblique asymptote here, y equals x, and going to make that broken like that so that you can see the boundary that it approaches but doesn't touch. Let's move on now to something a little different. Squared plus 16 over x. My oblique asymptote this time is going to be y equals x squared. So let's show you that. Like so. And I have a vertical asymptote at x equals 0 that I'll show you. So we've got x-intercepts at negative, I think that's negative cube root of 16. Zero is what it is exactly. You can round that to 2 decimal places if you'd like. I've got a local minimum right there at 212. I'm not going to have any y-intercept. My domain is going to be x not equal to 0. My range is going to be all real numbers here. And you're going to need, like I said, that extra point right there to help you figure out how low does it go. You can use your graphing calculator to get additional points to help you graph that. Notice that it's going to approach this curve though from the bottom here and from the top up here. Let's just prove to ourselves that this doesn't ever cross that. So if I get x cubed plus 16 over x equals x squared, x cubed plus 16 equals x cubed. I don't think so because 16 is never equal to 0. Now let's try x over x squared minus 16. We're going to get x-intercepts and y-intercept at 0, 0. We're going to have a horizontal asymptote at y equals 0. We have vertical asymptotes at x equals -4 and x equals 4. Let's put those asymptotes in. Go ahead and so, and see that the function is going to approach the horizontal asymptote from the bottom here on the left, and then approach that vertical asymptote from the left as it goes down towards -infinity. Going to approach the vertical asymptote from the right here as it goes towards +infinity. It's going to cross through 0, 0. Then it's going to approach this vertical asymptote from the left and go down to positive and go down to -infinity. It's going to approach the asymptote from the right that goes to +infinity. And there we go. You can make that little sketch of that graph. That one's not too bad. Now we've got x to the 4th minus 1 divided by x to the 2nd minus 16. So we have vertical asymptotes now at -4 and +4. Let's just factor this one all the way out. This is x squared minus 1, x squared plus 1, x plus 4, x minus 4. So this is x plus 1, x minus 1, x squared plus 1 over x plus 4, x minus 4. Again, that gives me x-intercepts at -1, 0, and 1, 0. Gives me a y-intercept at 0, 1 over 16. Gives me a oblique asymptote that I'm going to have to find by hand, but there's no horizontal asymptote because there's an oblique asymptote. There's vertical asymptotes at x equals -4 and x equals 4. To figure out that oblique asymptote, we're going to have to use long division of polynomials. So x squared minus 16 into x to the 4th plus 0x to the 3rd plus 0x squared plus 0x minus 1. The x to the 2nd, x to the 4th minus 16x squared, and change my signs and add 16x to the 2nd minus 1 plus 16. Change my signs and add. I really don't care about my remainder. I only care about the oblique asymptote at y equals x squared plus 16. So I'll put that on my graph now. And we'll make that red and broken. I'm going to have to zoom out some so that you can see everything that's going on here. Because there's a piece of the graph up here and a piece of the graph up here. let's see if my function is ever equal to my oblique asymptote, if it ever crosses it. X to the fourth minus 1 over x squared minus 16. Is that ever equal to x squared plus 16? So x to the fourth minus 1, is that ever equal to x to the fourth minus 256? It is not. So we're never going to cross the oblique asymptote. So we're going to stay within it, and this is going to approach the oblique asymptote on the left-hand side and approach my vertical asymptote. I didn't put my vertical asymptotes in here. X equals -4, x equals 4. Let's do that. And I'll zoom in on this area of the graph so you can see what it does. It approaches the oblique asymptote on the left and the vertical asymptote on the right. Then we jump down here when we approach the vertical asymptote here on the left-hand side of this, and the and this other vertical asymptote on the right-hand side. Don't forget that you want to find your x-intercepts and your extreme value. It looks like it's 0, 0, but it's not. It's really close to that. So make sure that you use your calculator to get that maximum is just a little bit above the x-axis there. Make sure that you use your calculator to figure out how far down these come. And notice that they're not quite parabolic. They're a little tilted. So make sure that you figure that out. And that's why you're going to need your calculator to graph most of these things. You're not just going to graph them by hand by plugging in a bunch of points and getting and figuring out how low is it going to go or how high is it going to go. All right. Let's work on number 46 now. The numerator is x squared plus x minus 12. And the denominator is x squared minus x minus 20. So, and our horizontal asymptote here is y equals 1. We've got vertical asymptotes at x equals 2. We're going to do some factoring and show you why there's a hole in this graph. It's kind of hard to see the hole. So this is going to be x plus 4x minus 3. And this is going to be x plus 4x minus 5. And so there's a hole at -4. X cannot be -4. So there's a hole at -4. And if I stuck -4 into the rest of this, that would be -7 over -9. So somewhere right here at -4 something, I zoom in here, function's going to be undefined there. It's just going to stop and say undefined when I get to -4. But that y value that it's approaching there is 7/9 right there. Okay. We've got the x-intercept there at 3, 0. You've got your y-intercept at 0, 3/5, which is 6/10. It's It's right there. And got all my asymptotes here. X equals 5 is my asymptote. And don't forget to put your hole on your graph at -4 7/9 for this problem. X squared plus 9x plus 20 divided by x minus 4 quantity squared. This one's going to look really funky because it's got a squared in the denominator. We're also going to be crossing our asymptote here. So I want to expand this out. This looks like this. If I want to factor it completely, it's going to look like this. So I may want both forms to help me. My x-intercepts are at -4, 0, and -5, 0. They're right here and right there. There's this other low point where it's going to turn. There's a local min at -4.47, -0.003. It's essentially 0, but it's not. So it's going to come down there and turn just below the x-axis. It's just going to have a little blip right down there below the x-axis before it turns back up. Let's show some of these asymptotes for you. Y equals 1 and x equals 4. Let's make the asymptotes a different color this time, so it's easier to see them. Okay, so we see that the function is going to cross through the asymptote right there, and I'm going to show you the math for that. So x squared plus 9x plus 20 over x squared minus 8x plus 16 is going to be equal to 1. X squared plus 9x plus 20 equals x squared minus 8x plus 16. X squared subtracted from both sides is 9x plus 20 equals -8x plus 16. Bring the 8x over to the left, bring the 20 over to the right, and x is equal to -4 over 17. And that's where this is a -0.235 approximately. And you're going to see that both of them are approaching a positive infinity here. They're having the same behavior on the opposite sides of the asymptote because that's an even multiplicity. There's no sign change on the two sides. So it's going to positive infinity here and it's going to positive infinity there because it doesn't cross the asymptote, the horizontal asymptote again. Over here, it's going to stay above it. It only crossed it this one time, and then it's going to come down, cross those two x-intercepts, and then it's going to approach the asymptote from below. Just a few more examples here. We've got x minus 4 times x minus 5 divided by x squared minus 36. There's an x plus 6 and an x minus 6 as factors in the denominator that don't cancel with anything in the numerator, so we're not going to get any wholes. We will get vertical asymptotes at x equals -6 and x equals 6. We'll get x-intercepts at 4, 0, and 5, 0. We'll get a y-intercept here at a positive 20 over a negative 36 is a negative 5 over 9. Zero comma. Let's see, that's a negative 20 over a negative. This is a positive 20 over a negative 36. Divide by 4. Divide by 4. Yes, a negative 5/9. So let's see here. There's my y-intercept right there. It's a little bit smaller than -1/2. We've got x-intercepts here at 4 and 5. We've got this little peak right here. There's a local max at 4.57, 0.01. We've got a local min over here at 7.87, 0.43. And are we going to cross our asymptote at all? Probably. This is x squared minus 9x plus 20 equals x squared minus 36. So, yep, negative 9x equals negative 56. X equals 56 over 9. It's a little bit bigger than 6. So if I put in my horizontal asymptote y equals 1, I'm going to see that it crosses it right there and then comes back and approaches from the bottom. I've also got vertical asymptotes at x equals -6 and x equals 6. Graph is never going to cross a vertical asymptote, but it can cross a horizontal asymptote. Let's look at x squared minus 4x minus 5 divided by x squared minus 4. Again, going to look at the factored form here, x minus 5, x plus 1, x plus 2, x minus 2, no wholes from this, because there's no common factors top and bottom. We've got x-intercepts at -1, 0, and 5, 0. We've got vertical asymptotes at x equals -2 and x equals 2. We've got a horizontal asymptote at y equals 1. We have a y-intercept at 0.5 over 4. It's right there, 1.25. Here's our one x-intercept, and our other one is right here. And we know that it is going to cross through at least one time right there, and that's going to be the only time that it's going to cross through. I'll prove that to you mathematically. It's 4x minus 5 over x squared minus 4 equals 1. Squared minus 4x minus 5 equals x squared minus 4. Add 5 to both sides. So 1, negative 4x, divide by negative 4, divide by negative 4, x equals a negative 1/4. So it's right there at negative 1/4. That's where it crosses through. And that's very close to the y-intercept, but it's not the same thing. So don't make it go through the y-intercept. It's a little to the left and below that. So you should be able to draw your vertical asymptotes, your horizontal asymptote. You should be able to draw this place where it intersects. You should be able to show that it approaches the asymptote from below as I'm over on the right, and from above as I'm over on the left, and that it's approaching this vertical asymptote here as I'm coming at -2 from the right, that I'm approaching a negative infinity as I'm approaching it from the left. I'm going to positive infinity. As I'm approaching +2 from the left, I'm going to positive infinity, and +2 from the right, I'm going to negative infinity. Let's look at our last problem for today in this section. F of x is going to be equal to x squared plus 3x plus 3x divided by x minus 4 quantity squared. So we're going to have x-intercepts at 0, 0, and -3, 0. That comes from factoring the numerator. The denominators are already factored. Got vertical asymptotes at x equals to 4. Degree of the top and degree of the bottom are the same. The leading coefficients are 1 and 1. So I've got a horizontal asymptote at y equals 1. Got a y-intercept at 0, 0. And let's look at the graph that's been provided for some additional information here. So let's stick y equals 1 on here as my asymptote. See how it's going to cross. I'm going to find that algebraically here. X squared plus 3x over x minus 4 squared. I'm going to set that equal to 1. X squared plus 3x equals x squared minus 8x plus 16. I'm going to bring the 8 x's over here. 11x equals 16. X equals 16 over 11. And that is approximately 16 over 11 right there. I'm going to have a local minimum somewhere right down here. Local min at -1.09, -0.08. It's going to cross the x-axis again and keep coming towards this asymptote. And there's going to be no local extrema on this one because it's always decreasing. So there you have it. There's some graphs of some rational functions. I encourage you to learn to use whatever technology you have available to you, whether that's your TI 84 or 83, and the second calc menu to find minimums and maximums or intercepts if you need that, or to use the Desmos graphing calculator here, or something like GeoGebra if your teacher uses that as an open educational resource. There's lots of tools that are available to you to assist you with sketching these graphs. Only use what's going to be available to you during your test, so that you know what you can use, and they use the same thing, practice the same way that you're going to be taking your test. All right. See you for the next video, which is going to be on quadratic or polynomial and rational inequalities. So talk about those next time.